prove the Sylow thing only, but I will state more general result. Okay, and then we will prove the conjugacy of Sylow subgroups. So conjugacy of or conjugacy of Sylow, or maybe I'll just write conjugacy and Sylow subgroups. Right. So what I will say in the beginning will just be like just a generalized version of it. Okay. And after that, I will prove the basic case. Okay. So the idea of the story is like this. You start with a group G. Okay. So this is a group. Okay. And then you have a field K. Okay. So K is a field. K field. Okay. I suppose, I mean, yeah, I have to assume that the characteristic is positive, but I'll just say any characteristic. If the characteristic is not positive, then this will not be interesting. Okay. Any characteristic, but I'm emphasizing any characteristic means that, yeah, characteristic P, so Z mod, ZP, and all the fields of characteristic P are included. After this, there is something which you construct, which is KG, and this is called the group ring. Okay, let me see there. This is the notation. So KG is the group ring. The group ring. So what is this roughly? Roughly speaking, it is the simplest ring that you can make out of K, out of a field and a group. Okay. So it is just that it is the group and there is also an addition. Okay. If I should define it and give you some exercises on this, I think it will be nice. So I'm just doing that.
While we are doing the group ring,
right. So group ring. Right. So group ring will be an interesting example of a ring. Okay. Group ring will be an interesting example of a ring for you. And what I will consider now is I will consider some modules over this ring. Okay, because we have done vector spaces, we have done modules a little bit. Modules over this ring. Okay, so then we will consider some modules over this ring. You look at the collection of all modules over this ring. And then what do you do? I suppose you have to, yeah, you have to fix a module, right? So then we'll consider modules over this ring. Then what we will do is we will consider a subgroup. Okay. So considering a subgroup and one second. Okay. Yeah. So if I consider modules over this ring, okay, then I will look at some subgroups, okay, such that module will become a nice module over those subgroups. Okay, I will be considering those kind of subgroups such that the module will become nice over these subgroups. Okay. And then among these nice subgroups, I will pick, certain nicer subcollection. Okay. Right. And so a certain nicer subcollection. And that nicer subcollection will become equal to the collection of Sylow subgroups of G for some special module M. Okay. So when I specialize to some specific module, which will be a trivial module, then for that trivial module, that subcollection which I was talking about, subcollection of subgroups, will be equal to the Sylow P groups, where P is the characteristic. Okay. And okay. So then you will get the things. But I will then prove that collection of subgroups, every subgroup is conjugate of another. I mean, I will not prove that, I just state that and then so that's the generalized setting. Okay, so that is, I'll just say the things, and this is probably not very important, but I will say it because that's the generalized, that's the setting in which it comes about. Okay. So right, so this group ring, let me just define for you. I mean, of course, we define it using some things called universal properties, but if we give a simple definition, then right. So you can just look at group ring as, so this thing is a vector space, okay? And this also you can assume it's a finite group. Okay? Yeah, it's a vector space. Do we need finite group? I think yeah, we can assume finite. Right. It is, these have to be finite. So KG is a vector space. Okay? And these group actions can also be said in terms of modules over KG. So yeah. So what is KG? Let me say. So KG is a vector space with G as a basis. Okay. So G is a basis and KG becomes a vector space with respect to that. And then we will, then you define this right. Then you define a multiplication in, because it's a ring, right? So multiplication in KG is bilinear extension of, I'll just give an example of multiplication in G. Okay, I'll give an example. Group rings are going to be very important because see, why do we study groups and why do we study rings? I mean, we want to algebraize a situation. So you have a situation in which your addition and multiplication is not available to you. For example, symmetry, studying symmetry. I mean, usually people don't think of multiplying symmetries, but when you think of symmetries as groups, then multiplying is probably the only thing you know. Okay, so you algebraize the situation, and this KG is sort of like mathematics for mathematics. Okay, so KG is an algebraization to understand groups, which themselves are algebraizations to understand some real objects. Right, so it's one step in that abstraction. Okay, one can think of it like bilinear extension of multiplication in G. So what do I mean? I mean, so let's take X and Y in KG. So how does it look like? Obviously, this X will be, as I said, vector space with basis as G. G is a basis, which means the elements of G are basis elements. So, you know, like you could take G1 plus 2G2, let's say this is X, and Y is, you know, G3 plus 5G2, something like this. And how will the multiplication be defined? It will be defined in the most obvious way. Okay. As I said, bilinear extension, right? So, can there be any problem? No, there cannot be any problem. But that you don't have to think right now. But you have to just know that the multiplication is the obvious one. There won't be any problem because this is the basis. You see what I'm doing? Just the usual thing. Just like you multiply polynomials. Right? Now you can check for homework that this group ring is in fact a ring. Okay? Group ring is in fact a ring. this group ring is commutative if and only if the group is commutative, and things like that. Those are obvious. Right. So yeah, this is the definition. And one more homework is this. Yeah. Find a group G such that the group ring is equal to the polynomial ring. This group G is a standard group, if we just think, and this will also tell you that group rings are also encompassing the theory or encompassing this containing as subsets examples of polynomial rings. So that's very interesting. So these are very interesting objects in that. Yeah. So this is another homework, and you can of course read more about this on the internet or books. I don't know if it is there in Artin. You have to check. Other books are there, but though maybe not needed. So do this homework, and this will make it. So yeah. Okay. So the concept of group ring is okay, right? From a group, to understand a group better, you make a ring out of it. So you add a further algebra structure, which is addition. Group has only one structure, right? And this is like the willingness to extend it. Right. All this will be very fruitful. So let's move. Yeah. So think of group ring in the simplest way. So this is a group ring. Right. Okay. Now think of it. Now think of this. Okay. Fix, and so this will be fixed. Okay. Fix a module M over kg. So kg is your ring. So kg is your ring, M is your module. Okay. So this you know. Fix this module, and then let's write. Okay. Now let us think of this. Okay. Take this example. Okay. Suppose V is a vector space over K. Okay. V is a vector space over K. I will compare this there. So V is a vector space over K. And yeah, I mean, let's say there are two vector spaces. Now suppose, and this you should be able to prove, suppose that you have a surjective map from V1 to V2. Okay. You have a surjective map from V1 to V2. Okay. And this is obviously, when I say map, I mean linear transformation. So you have a linear transformation from V1 to V2. Okay. Then surjective. Then there exists a transformation T1, which is from V2 to V1, right? And this is, you will see that this is just, I mean, it's just going to be very simple. So such that T1 composed with T2 is equal to identity. Identity, it will be identity on V2, right? Yeah. So let us just quickly prove this. Yeah. Or let me just see. So linear transformations, you know the definition, right?
Yes.
Between vector spaces, right? Then you should take it as an exercise. Okay. That, and this is actually very important. Okay. So whenever you have a linear transformation which is surjective in this direction, then actually there is a map in the other direction, such that first you go by that map and then you come by this way. It's actually going to be identity, and it's a very simple thing actually. So suppose you take a basis of this. So all these are all the maths that you know, college maths, sort of everything comes here. Okay, in a way, I mean, yeah, we can also bring in the geometry part also, the analysis and all you've done, but we are just not doing everything at the same time. So, yeah. So this thing, and then you see the maybe b1 prime, bk prime. Okay, and there is a surjective map. Surjective map means that basically there is a map, right? So this b1 goes to some b1 goes to some b1, or maybe I will just write like this. Let's say this is tb1, this is tb2, right? And this is tbk, correct? Or rather tbn, right? So this is surjective map means what? It means that this tb1 to tbn is a generating set for v2, correct? Because I mean that will generate the image, right? And the image is v2. So tb1 to tbn is a generating set for v2, right?
Yes.
Right? I mean, obviously you have to write a proof, but I just whether you can feel that it is correct. I'm not saying that you have proved it. Maybe you have not proved it before, so you don't know. But right. But then that means that there is a basis contained in this, right? Some subset is a basis, because every generating set contains a basis. So every generating set contains a basis is the magical thing, is which you already know, right? Now that you have a basis, what do? How do you define T1? Obviously just reverse, right? Send this thing to BI1, right? Send this thing to its BI2. Similarly, send this thing to BIK. And you have sent a basis from V1, you have sent. And so everything, so you have decided the whole transformation T1, right? Because you've decided its image on a basis. So T1 is defined, and you can check that first you go by T1, TB1, T of BI1 goes to BI1, but BI1 again goes to T of BI1. So it's identity. One composition is identity, other is not. Okay. So this is just a rough sketch. Now you should prove it, or first review your knowledge of linear transformations, then prove it. But it's a very essential exercise. And obviously, if you already know this probably from even before, that if you replace this thing by sets, then it is always true. Surjective function will always have a right inverse. That is actually a definition of, can be taken as a definition of surjective function. Okay. But anyways, so that's just the short thing. Okay. Right. But this kind of thing doesn't happen for modules over rings. If you have a module over a ring in which you have a surjective map, it doesn't imply that the reverse map will be that there will be a reverse map such that the composition is identical. It doesn't happen for modules over rings. You can take some simple example. Let's take an example. Better. So you see all of this is getting cut out. So you have to prove this. Yeah. But yeah. So let me just give an example. So I want to give an example of a module which is not projected. Right. So exactly. So you just do this. You look at Z. Just take your standard stuff, right? And this will also be a homework. Look at this. This is surjective map, right? So these two things are Z modules, right? Z is a Z module and Z mod 5 is a Z module, right? Because you will define the action. So means, right? So this is a Z. This thing is also a Z module. Means you can multiply Z. You can consider a scalar and multiply. Okay, right? And this is the natural surjective map is this. Right? Just take some integer and then send it to modulo 5. Okay, so you have this map. But obviously, you don't have any other map in the other direction, right? So you take this map pi. Okay, pi is a Z module. Just in place of field, we are writing Z. In place of Q, we are writing Z. There is no other. Is a Z module map, So this is like your T. This is your T. But there is no this and you can prove this. There is no this. I mean, this is a 5-element set, right? You can obviously prove there is no map to Z. There is no pi prime which is from this. I mean, in fact, there is no map other than the zero map. There is no map. So forget about composition being identical. There is no map like this other than the zero map. So not possible, right? So I'm just showing you the two extreme situations because that will be needed in this concept. Okay? The two extreme situations you understand, right? So we have similarity between the situations is that both are modules over rings. This is a module over a ring, which is a field. This is the case a ring. This is also a module over a ring. So that's a similarity. Okay. What's the other similarity? That yes,
what's the similarity?
That both of them are modules over rings. Vector space is a module over a ring, right? Where a ring is a field. Right. A field is a ring, right? So that's not a, so it's a special case, right? A vector space is a special case of module over a ring. Right. A very special case, but it's a special case. Okay. And this is also that, so that's a similarity. Obviously, that's a basic similarity. The other important similarity, that's like a standing hypothesis similarity. Other similarity is that both of them are surjective maps. Yeah. What's the difference? On one side, you always have a map in the other direction. That's a very important property of surjective maps. You should prove it. Okay. Very important property of surjective maps. Okay. And in this side, there is no map in the other direction. That's the difference. And that's a big difference. Okay. Now we are going to introduce a concept based on this. Okay. Maybe I will not introduce a concept. I will just say the situation because the concept will involve more words called a projective module. But then that will take long time. So I just want to, because I want to be done with this, and I just want to show you that the Sylow story sits in a bigger story, where it is actually, maybe things become more transparent provided you spend time. But before that, it looks more obscure actually, which probably is looking to you right now. But you will see if you prove all these things, and it all connects back when you read more about this. Okay. So, anyways, you look at this. Now you come to this. Okay. Now we'll see the situation. So, right. So, if right, because M is a module over a ring, if you take some other module N and you take a surjective map T, it may not have a left inverse. It may not have a left inverse. Correct? That we already saw example, right? It may not have a left
inverse. Yes.
Right. It may have, but it may not have also. Okay. So, okay, maybe I'll just keep this here. There is no need to erase everything. So T may not have a left inverse. Okay. Now comes your group theory language. Okay. Pick a subgroup H. Okay. Pick a subgroup H. Now look at the same thing. Now pick a subgroup H and look at KH. Try to feel. This KH is also a group ring, and no doubt you can understand that KH sort of sits inside KG. Right? KH is a smaller thing than KG. Sits inside clearly. Look at KH. Okay. This T is a module morphism from N to M over Kg. What does that mean? It means, as you know, that T of Rn is equal to R times, just like vector spaces where R is in Kg. But it means that if R is in KH, then also this will be true, right? So basically that same morphism is applicable in this over this ring. We have changed the ring. We have come to a smaller ring, right? over the smaller ring also this morphism makes sense, right? It's still surjective because being surjective is a set theory property that doesn't change, but it's still a morphism because they want to a smaller ring. So when to a bigger ring, it may not be a morphism anymore. So that's the problem. But here it's obviously true. If it's true for all R in KG, it's true for all R in KH. That's the basic. So now you basically, I'm saying, look at this. Now, T again may not have a left inverse, but the chances are that it might have a left inverse. The chances have increased, right? Right inverse.
KH is a subgroup of KG or subring or
Subring. H is a subgroup, so KH becomes a subring. Right.
Okay, and what does the K stands for?
K is the field, right?
That's R or K?
K. You can take it to be R also, I don't mind. But
Okay,
you have to take it to be K. No, actually don't take it to be R because we need Sylow groups, right? We want to talk about, so you want a characteristic. So if you take R, then it has characteristic 0, which is not useful.
Okay.
We want fields with characteristic T. Okay, so Z mod ZT and so on. Then the story can come. Now the point is that now chances have increased that this has a right inverse. Because you have gone to a smaller place, which is more like a field now. I mean, the H is becoming smaller and smaller. When the H becomes trivial, if you take the trivial group, then it becomes K. And then actually it has a right inverse because it has for vector spaces. True or not? If you take the H to be identity, if you go to the last case, then this has a right inverse. True?
Yes, it has.
And so what I'm now trying to show you is there's a spectrum, right? As you go down, the probability that it has a right inverse increases.
Yes.
Okay, so that is what I am trying to say. Now, so it is clear that there is a place where everything will have a right inverse. Okay, that is what I'm saying. That place exists. Okay, all right, but we are not interested in that. That I said because it's easy. It's like sort of like easy because quite true. But what we are interested in is a subgroup H, or maybe H prime, such that we want a subgroup H prime such that if this same T has a right inverse, this is called a retraction, has a right inverse in this, okay, then T has a same right inverse in what's a non-trivial thing? In kg. Because नीचे जाने से तो right inverse will remain, so there's no need of talking about that. But the other thing, so we are interested in that place, which is sort of the nice place where whenever you have, so you go to that subgroup, okay, such that in this subgroup, it's a very interesting subgroup because whenever T has a right inverse, any surjective map has a right inverse here, it also has a right inverse in the bigger case, which is not always true, but we want that subgroup. Can you give an example of that subgroup? Well, just take H prime to the G, it is true. That's a funny joke, right? I mean, if you take H prime to be G, then it is true. Why? Because then the statement becomes a tautology, right? If T has a right inverse in Kg, then it has a right inverse in Kg. That's always true. So what do you want? You want a minimal such subgroup. Because you already have a subgroup like that, which is a group itself. We want a minimal such subgroup H prime, such that that's because G per NA say it is true because G is G. थोड़ा सी नीचे जाने से maybe it is still true. कुछ anything that has an inverse in this, it has an inverse in that. But जितना नीचे जा सकते हो so that there also it is true. कि यहाँ पे inverse होगा, then there also it will be inverse. You want a minimal such subgroup H prime. Okay. Now you look at the collection of all. Look at collection of all such H prime. Okay. And the claim is that these are all conjugate to each other. Okay. This is called a vertices. Vertex is called a vertex of M. Okay. And then the claim is, and now I will, claim is the collection, this is a collection of subgroups aa gaya. Collection of all such, this is how mathematics comes. All such subgroups are conjugate. You remember that the G was fixed, the M was fixed. After that we were talking. Okay. Yeah. And any such subgroup is actually a P group. Okay. And any such, okay, any such H prime is a P group. Which means, power is P. Okay. So if you call this collection C, right? So you understand how this collection is coming?
I have a question.
Yeah.
The transformation we are giving from N to M,
Mhm.
they are different modules
Right,
over kg,
right.
and both are modules over kg, or one of
Yes.
them over kh also?
No. Both have to be over kg, otherwise this will not make sense.
Okay.
Yeah. I mean, I have skipped a lot of details, but yeah, but this one is clear that it has to be over kg. Okay. I mean, even this is incomplete what I'm saying, but yeah.
And how it will look like?
Yes, that is the problem. Yeah.
Something more about the modules, I'm very confusing.
Yeah, it is confusing. Yeah, maybe with more group actions I can explain later. But all I wanted to show is that you have a collection of P groups. C is the collection of, yeah, because right now you are kind of starting in these things. So C is a collection of P groups, and every element, and there is only one conjugacy class. Okay, and all of them are conjugates. Okay. Now, if you take M to be special, then C becomes, so you see the collection of P groups, right? If you change the module, the collection will change. So if you change the module M, that's what the deal is, then you can actually make C the collection of maximal P groups, which are silos. And then this theorem, this claim will imply that. Okay. That's what I'm saying. Yeah, let me just see. If K is a field and G is a finite group, then yeah, for the trivial, yeah, if you take something called the basic, the simplest module, if you take, then the groups will become silent. Okay. So a suitable module makes C the collection of Sylow subgroups, and then its conjugacy comes from this. So basically the point is that the fact that Sylow subgroups are conjugate is a special case of the fact that there are a lot of collection of P groups which are conjugates, or P subgroups which are conjugate. And Sylow subgroups being conjugate is a very special case of that. And that is why the proof of Sylow theorems maybe looks a bit strange sometimes, because it's a specific example of something proper. Anyways, we'll meet after 10 minutes maybe, and then we'll prove the Sylow theorems. We'll not prove this maybe. Maybe not today, later we can. But this is the picture.